Okay, we got a really short video. I told you I would try to get them short. Now I'm going to milk this one for everything it's worth. Here's my short video for you. Just a few things to add to your notes. This is still section 3-2. We're still talking about variation, and we'll actually continue this for some more this week. Okay, so what we're looking at right now is the coefficient of variation, or the symbol that they use for it is CVar. And what the coefficient of variation is it's used to show the difference between two, or show how similar two standard deviations are if the standard deviations are measuring two separate things. Here's what I mean by that. When you are comparing standard deviations, and let's say both standard deviation measured, how about let's use the example from yesterday. How many automobiles were sold in Europe? And we were looking at, let's say, automobiles sold in Europe and automobiles sold in the United States. They're both measuring number of automobiles sold. So when you're comparing the standard deviations, you're comparing apples to apples. You're comparing two of the same measurements, automobiles sold. Now, when you're comparing two different things, such as if we went around and we wanted to find out how much do the number of hours a student studies and their grade in the class. So we went around and we asked a bunch of students, hey, how many hours do you study per night? And we asked, hey, what's your percentage in the class? And we gather all that data and we do our variation tests on both sets of data. So we find our variance and our standard deviation for the number of hours that they study. And we find our variance and our standard deviation for their percentage in class. We want to find out what varies more. And remember, variance is just how spread out the data is. Okay, how far away from the average is it? And if we wanted to kind of compare the two, it wouldn't work very good, because one of them is how many hours they studied, and one of them is a percentage. You can't compare those two. What the coefficient of variation allows us to do is to take both numbers and turn it into a percentage. And now this percentage you can compare to each other, and now you're comparing apples to apples. You're comparing two percentages. Okay? So the way that we find this CVar is we take our standard deviation divided by the mean. And we have two different formulas here. They're the same formula. It's just that this one is for the sample and this one is for your population. Again, standard deviation, either it's the S for the sample or your lowercase sigma for population. X bar is your mean for sample. Mu is your mean for population. Okay. So we use a CVar to compare standard deviation when we're talking about two different sets of units, two separate sets of data that are measuring two separate things. Okay. For instance, if we were talking about the number of sales of cars over a 3-month period, and we were talking about how many commissions, what the amount of commission that these automobile salesmen made. So if you were a car dealer, you would think that, hey, the more cars I sell, the more money I should make as commission. So we want to find out, is that comparable? Are the two, do they vary at the same rate? Well, how do we compare the two if one is measuring number of cars sold and one is a dollar amount? It doesn't work very well. So what we're going to do is we're going to turn both of those numbers into a CVar, a percentage that will allow us to compare. So for the sales, we take our standard deviation, which is 5. We divide it by the mean, which is 87, and multiply it by 100% to get 5.7%. When we do that same thing, we take 773, which was a standard deviation for the commissions, divide it by the mean, which was 5,225. Multiply it by 100%, we get 14.8. So which one varies more? Commission is almost 3 times as much. Okay? So what that's saying is a car salesman's commission can vary more drastically than the amount of cars that they sell over a 3-month period of time at whatever car dealership they went to. Okay. So a car salesman does, because of that, can't say, well, if I sell more cars, my commission's going to go up. This shows that there are more, there are different things that kind of play into that. It's not always just sell more cars and you make more money. Last thing, it's called the range rule of thumb. And what this is, and you have to be very, very clear on that, is this is a very broad approximation of the standard deviation. Okay? It's not something that we like to use a lot. It's not something that you want to use for very detailed, when you want to talk about something in detail. It's something that's it's a quick estimate. And what you do is you find the range and divide it by 4. And that is your range rule of thumb. So it's an approximation of the standard deviation. I can't tell you how close it will always be because it depends on the situation. What we do want to make sure is that we're using a unimodal. Remember, that's data with only one mode, and symmetric data. It doesn't have to be perfectly symmetrical, but the more symmetrical it is, the closer that this approximation will get. Remember, symmetric is like a bell curve where you have, let's see if I can get, a very nice bell curve where you have your mean right here, and about half the data falls to the right and half the data falls to the left. Finally, what you can do with that range rule of thumb is that if you take your mean and subtract 2 of those, you can approximate the lowest value. If you take the mean and add 2 of those, you can approximate the highest value. Here's your sample, or for example, if our mean was 10 and our range was 12, our range rule of thumb would say that we take 12 divided by 4, and we get a value of 3. So that's our standard deviation, very approximate value. If we then take our mean and go 2 below and 2 above, so that's 2 times our standard deviation below because we're subtracting. Our low value is 4, sorry. And if we take our high value, our mean plus 2 times that standard deviation, we would get approximately our high value, which is 16. Again, because this number is approximate, we can't be guaranteed that these numbers are perfect, but they should be pretty close. Again, it's a quick approximation of the two. That's your notes. Make sure you submit your pictures of your notes, and we'll see you tomorrow.